So let's start thinking about the question about how you would even start to describe the motion of a point along an arbitrary path like this one. Or maybe like this one, moving around in a square. It's not the kind of thing that you're used to seeing equations be able to do. So if we're going to represent a path, you can see I've graphed it here with little arrows to indicate not only what geometric shape the curve makes, but also the direction of travel if we have something moving along the curve. So what would be conceptually nicest is if we could define a function like this. The input would be some time in seconds, and the output would tell me both the x and the y coordinate for where I am at a certain time. So I could say then, like at time equals 0, I start out at 1, 1. And then when time equals 10, I'm at 11, 1. And then when time is 20, I'm at 11, 11. If we could define an equation that defines a function like that, at least we can't imagine what that would look like necessarily, but at least conceptually that is the sort of thing that we'd want because we are mapping times to locations. And that seems ideally suited for describing a path. So what we actually do is we split a function into two separate functions. We'll have one function that describes just the x position as a function of time, and then another equation that describes the y position as a function of time, and each of those get their own equation. So in this example, we'd have something like this. Whatever this equation ends up looking like, I know that when time is 0, oops, not 0, when time is 0, the x-coordinate is 1. And then when time is 10 seconds, for example, the x-coordinate would be 11. And then when time is 20 seconds, the x-coordinate is still 11 because we've been moving up during that time, so the x position hasn't been changing, and so on. So we're going to try and find an equation that only describes the x position of this movement. And similarly for the y-coordinate. When time is 0, the y-coordinate is 1, and it continues to be 1 until time is 10, when I get here. Then when time goes from 10 seconds to 20 seconds, my y-coordinates start going up from 1 up to 11, and so on. Okay, so let's not jump to equations yet, because that's often tricky to think about. Let's think about a graph. So if I just wanted to graph the function that tells me my x position, I can put in the key points that I know at different times. So at time 0, the x-coordinate is 1. Then the x-coordinate increases to 11. Then the x-coordinate stays at 11 the whole time as I'm moving up. Then the x-coordinate goes from 11 down to 1. And then the x-coordinate stays at 1 the whole time as I'm moving down. So if I put these together with lines, we'd want a function that looks like this. So take a minute and look at the graph that we drew by hand. Is there on the lower right-hand corner. The x position is a function of time. And I've also got the y position as a function of time. And you can see as time is increasing, both the x-coordinate and the y-coordinate in their own graphs, but also in the overall parametric path that we're tracing. Look at them separately. So watch when it gets back to its starting position. X-coordinate goes up, stays the same, goes down, stays the same, goes up, stays the same, goes down, stays the same. And let's do the same thing for the y-coordinate. So here the y-coordinate starts at 1, stays the same, increases to 11, stays at 11, and then decreases back down to 1. So hopefully you remember from last time how to use a piecewise defined function to represent equations like the x position and the y position. And I'm not going to go through a full derivation of those here, but I'll show you what the answer looks like. Here it is. So don't worry too much if you think that you're maybe a little bit rusty making piecewise defined functions for this. But what I want you to take away from this video is the idea that we're going to be describing paths using separate equations for the x position and the y position. As a check for understanding, let's pretend that we have a different function describing the x position, where the x position starts at 11, goes to 1, back up to 11, back down to 1, and back up to 11. So the y position is the same as before. What I want you to notice is that all of the x and y positions move between 1 and 11. So we're going to have a path that visits the 4 points that are shown here, A, B, C, and D. But instead of going in a square, they're going to go in a different ordering. So what I want you to do is figure out what order do we visit the points in? Which point is first, and next, and next, and next. And here's the answer. At time 0, we start at B, go to A, C, D, back to B again.